Good morning, student. Today we are going to learn about Seeley detector. It is a FM detector. After the completion of today's session, you are able to draw the diagram of the Seeley detector and explain operation of Seeley detector. Seeley detector. Let's go to the diagram directly. It is easier for you to understand here. So this is the circuit diagram. This circuit consists of an inductively coupled double tuned circuit in which both primary and secondary coils are tuned to the same frequency. The center of the secondary coil is connected to the top of the primary through a capacitor C. So center, this one is the secondary coil, center of the secondary coil connected to the top of the primary through a capacitor C. This capacitor used as a coupling capacitor. It blocks the DC from primary to secondary, and also it couples the signal frequency from primary to the secondary. Then the primary voltage V3 appears across the inductor LP. This one is the inductor LP. So the V3 appears across this inductor. Okay. Then nearly entire voltage V3 appears across inductor L. See here. Except a small drop across the capacitor C. Okay. Then the center tapping of the secondary coil has an equal and opposite voltage across each half of winding. Hence, V1 and V2 are equal in magnitude but opposite in phase. The radio frequency voltages, that is VA1 and VA2. So what is this VA1 and VA2? That is applied to the diode D1 and D2. So VA1 equal to V3 plus V1. Okay. This V3 and V1. Similarly, VA2 equal to V3 minus V2. As already we discussed that V1 and V2 are equal in magnitude but opposite in phase. So VA1 is V3 plus V1 and VA2 equal to V3 minus V2. Okay. So this VA1 and VA2 applied to the input of the D1 and D2. So the voltages VA1 and VA2 depend upon the phasor relations between V1, V2 and V3. The phase position of V1 and V2 relative to V3 would depend upon the tuned secondary coil at resonance and off resonance. Means here we have two conditions, that is one is at resonance, other one is off resonance. Okay. So first we discuss about at resonance. When an input voltage has a frequency equal to the resonant frequency of the tuned secondary. Okay. When the frequency of input voltage is equal to the resonant frequency of secondary, then V3 is in phase quadrature with V1 and V2. Phase quadrature means 90 degree. So here this one V1, this one V2. So these are phase quadrature with V3. Okay, so the resultant voltage, that is VA1 and VA2, okay, are equal in magnitude. Here we can see the phasor diagram and we can observe it easily that VA1 and VA2 are equal in magnitude. Next we discuss about the condition of resonance. So in off resonance, when an input signal frequency is above the resonant frequency, then the phase difference between V3 and V1 is 45 degree. Means this one is the V3 line and V1 is 45 degree angle, makes a 45 degree angle, because V2 is in phase opposition of V1. The phase difference between V3 and V2 is 135 degree. Okay, this one is the 45 degree. This is V1, this is V2. The phasor diagram reveals that VA1 is reduced whereas VA2 is increased. The situation is like this. See here, when we draw the resultant voltage, that is VA1 and VA2, here we can easily observe that VA1 is reduced whereas VA2 is increased. Okay, then when an input signal frequency is below the resonant frequency, then what happened? The situation is reversed. So at that time V3 here, V1 creates or makes a 135 degree angle with V3 and V2 creates, one second, this is 135 degree angle and V2 makes a 45 degree angle with V3, that is V1 and V2. So when we draw the resultant voltage, here we can easily observe that VA1 is increased and VA2 is reduced. Okay, so this is all about phasor diagram. Next, the voltage VA1 and VA2 are separately rectified by the diodes D1 and D2 respectively to produce V out 1 and V out 2. So at the output we get V out equal to V out 2 minus V out 1. Okay, so this is all about the working of Foster-Seeley detector. Thank you.